Every summer, a section of the ocean floor the size of New Jersey goes silent. The largest dead zone in the United States forms every spring in the northern Gulf of America. In 2025, it covered over 4,400 square miles of the seafloor. These are called hypoxic dead zones, areas where dissolved oxygen drops so low that marine life faces a choice between fleeing and dying. But how does that actually happen? Step 1. Nutrient pollution. It starts on land, not in the ocean. Excess nutrients that run off land are piped as wastewater into rivers and coasts can stimulate the growth of algae. The main problem are nitrogen and phosphorus, which are both found in fertilizer and animal waste and in emissions from burning fossil fuels. On average, about 20% of nitrogen fertilizer is lost through either surface runoff or leaching into groundwater. Step 2. The algal bloom. Algae feed on the nutrients, growing, spreading, and turning the water green. Algal blooms can smell bad, block sunlight, and even release toxins. Chemically, algae use nitrogen and phosphorus to fuel photosynthesis. The simplified reaction looks like this. During the bloom, the algae are actually producing oxygen, which sounds good until the algae die. Step 3. Decomposition. As the algae die, they are decomposed by bacteria. The process of decomposition consumes oxygen from the water, resulting in areas of hypoxia, otherwise known as dead zones. This decomposition reaction is a form of aerobic respiration. Massive amounts of dead algae leads to massive amounts of bacteria, which ultimately results in oxygen getting consumed faster than it can be replaced. To consume all the dead algae, microbes have to use a lot of oxygen, and in the case of dead zones, nearly all of it. Step 4. Stratification. So why doesn't the ocean just refill with oxygen? The bacteria that cause decay use oxygen dissolved in the bottom layers of water. As long as these layers of water are well mixed with oxygen-rich surface waters, the oxygen is renewed, and dead zones don't happen. However, the configuration of warm surface waters over cold floor waters is stable, meaning that in that scenario, there is little vertical mixing, and therefore little renewal of depleted oxygen. While this does occur naturally in the spring and summer, climate change has made this worse. Climate change's role. This is where greenhouse gases tie in. Climate change drives hypoxia through 3 compounding factors. First, oxygen is less soluble at higher temperatures, so as our waters warm, they don't get the oxygen they need. Second, marine life consumes more oxygen at higher temperatures, as higher temperatures raise metabolic rates. Third, as mentioned before, higher temperatures increase stratification. Open ocean areas with depleted oxygen, including areas that are not hypoxic yet, have grown more than 1.7 million square miles in the last 50 years alone. And coastal waters have seen a 10-fold increase in low oxygen areas within the same time frame. This is also a feedback loop. Ocean warming reduces oxygen solubility and increases water stratification, which promotes methane-generating anaerobic microbial processes. This creates an out-of-control loop where climate change encourages more greenhouse gas emissions from aquatic systems. If the dissolved oxygen concentration falls to hypoxic levels, organisms will begin to avoid or migrate out of the area. Mobile animals like fish and crabs flee. Immobile ones like shellfish, corals, and some floor-dwelling invertebrate simply die. Dead zones are therefore often accompanied by a decrease in biodiversity and a collapse in benthic populations, lowering the diversity of yield in commercial fishing operations.